Well, thank you very much for the invite to give this prestigious Ockham lecture. And what I hope to cover this evening is where we've actually got to in the development of a completely new type of propulsion system. One of the things that I heard over the conversations earlier is that there are a lot of physicists here, so I will pause at some point and talk about entropy. I love to do that because if it's an audience of engineers, they go absolutely pale, and when it's an audience of physicists, they go just a little bit pale when you sort of talk 6 years of access to space. Looking around this audience, most of you think that access to space is ancient history, but unfortunately it sort of happened mid-career as far as I'm concerned. And the launches were derived from the sort of Cold War technology that we developed to keep one another at bay, and unfortunately it looks like we still have to do that to some extent. So they've been really, really faithful friends, and I'll come on to that in a moment with regard to the whole new vista that they've opened up with regard to our understanding of the solar system, the way that they've impacted our life on Earth every day. All of you are influenced in ways that you probably don't even realise because of access to space. Of course, in many respects, the Russians set the whole thing moving with the launch of Sputnik 1 in 1957. And prior to that, when I was sort of in my teens, we were looking at the Americans for launching something weighing about 18 pounds into orbit. And all of a sudden, in October 1957, the Russians launched something weighing 180 pounds into orbit. And everybody said they dropped a decimal place somewhere. It won't be possible, but not true. So this was originally designed to deliver very large atom bombs onto the West, because the Russians didn't know how to make small atom bombs in those days. But from that, everything has grown. Okay, well you can see that that's really the same sort of vehicle that we've got here. And it's got upper stages and so on. This one was Black Arrow, this one was British. Now, we've got a unique record in Britain in that back in 1971, we developed this launch vehicle in the previous sort of decade, launched one satellite, Prospero, and then thought, oh, this is too easy, and got bored with it, and we've never launched another one since. We cancelled the rocket straight away as soon as we knew it worked. We launched 4 of them. And I was in Australia in 1969 when we launched the first one, and the launch site was such a mess that a manhole cover flipped into the propulsion belly, cut some of the controls, and the rocket sort of had a bit of a struggle until we finally cut it down. A very spectacular explosion at 50,000 feet in order to get rid of it. And of course the space shuttle, which is now defunct, but through, I guess, most of your lifetimes was the mainstay of getting into space. So the space shuttle has been with us, done its job, and has now gone again, unfortunately. And the Americans find themselves in the embarrassing position at the moment of having to use this, the Russians, to get them up to the International Space Station, which they largely funded and built. So across this period, a huge change has taken place in how we get into space. So what has happened in all of this? Of course, a huge expansion of knowledge, and I know that there are some very renowned astrophysicists sat in the audience who will know all about this sort of stuff more than I do. But of course, there is a permanent population in space as well. The human race over the last sort of century has expanded from the surface of the Earth, so that up to about 50,000 feet, there are something like several million people in the air all the time. The human race is no longer stuck to this 1D plane on the surface, and it extends to a handful of people up to about 300 kilometers in space. So the human race is slowly diffusing off the surface of the planet. And of course, images of the planets. If you dig out a typical astronomy textbook from 1955 and have a look at what we know about Mars or Saturn or Jupiter at that time, and then compare it with what we know today, no comparison. Wonderful. And of course, there are other much more tangible benefits in our lives. So you can drive into all kinds of rivers and floods with your GPS system. And we can broadcast the Olympic Games all over the world from London. So the world is shrinking, the communities are coming together, and one would hope that sooner or later we'll all learn to realise that this is a really tiny place and that we can't afford to muck about on it the way that we currently do. The problem with rockets is that they are basically military hardware brought into modern life. A rocket arrives at a launch site as a large airfix kit of parts, which you put together. Massive number of people. In order to get a shuttle into the air, it took about 6,500, at its peak about 10 or 11,000 people, just to put it together and get it into flight. And that cost of the order of, we don't know the precise numbers, between $500 and $700 million for each launch. And with our current Ariane 5, which is the sort of gem of the European space program, each launch of that is about $180 million in round numbers. And of course, that rather limits what you can do in space. As a consequence, there may be between 50 launches a year, and maybe in a really, really good year these days, 100 launches a year. And so, at that rate, the diffusion of the human race off the surface that I mentioned is going to be incredibly slow, and we need something better. Now, in Britain, we've got, as I said, a rather interesting history. My career sort of began at Rolls-Royce working on Blue Streak. Back in 1969, I was out in Australia looking after a set of engines to go into this vehicle, and witnessed the flight of one of those. I've already said I saw the first flight of Black Arrow. So in the sort of 60s to 70s, I learned quite a lot about sort of rockets. But back in the sort of drawing room up at Preston, British Aircraft Corporation was studying something really exciting, and that was a stack of rather similar looking aeroplanes that would lift off as a single unit. At a certain altitude, these would separate, these two stages would be transferring fuel into the core during the launch, and then this one would go onto orbit, deliver about 5 tons of payload into a low Earth orbit, re-enter, and then fly back. So within a few hours of the launch, you've got 3 separate aeroplanes back at the launch site to put together and do it all again. That would have brought around about a major improvement in the way in which we gain access to space. It would have really transformed it. But unfortunately, this all arrived at a time when Britain was starting to lose interest in this sort of thing. We'd had the wits scared out of us by World War II. And so in the sort of 1940s and 50s, we put a lot of effort into it. By the 60s, we were starting to face economic realities. And then in the latter part of the 60s, the Wilson government came to power, reviewed all that we were spending on aerospace, and decided that we really couldn't afford to do all that. There's a long story there that I don't have time to go into. But in the 1980s, this came about. Now, Steve mentioned that I spent a few years during the early 70s working for British Aircraft Corporation, working on things that can't go into in much detail, but were very much tied up with national defence. And as part of my conditions for working there, I used to have every Friday afternoon with their computer, which had massive capabilities. I think it was an IBM 1160 or something. And I mean, this had got a sort of central processor with 32 kilobytes of core, and we've got stacks of card readers and so on. And I was allowed to use that to do whatever I liked on, which was quite an achievement, because the rest of the time I was shut literally behind bars in locked rooms and I couldn't talk about what I was doing. And I investigated all kinds of propulsion systems, and all of those studies led me to the conclusion that rockets really were not going to hack it in the long term. And we had to start to do something different. We had to use the lower atmosphere like a jet aircraft in order to offload the problem of the rocket. Now, a rocket's an exponential device in terms of its weight. When you launch a rocket, the first part of the propellant you burn is putting the energy into the propellant you're going to use later on. And so there's quite a famous equation called Tsiolkovsky's equation. And basically, it's an exponential relationship between the starting weight and the finishing weight of the rocket and the exhaust velocity engines. Rockets cannot quite hack it because we can't make the structures light enough. Get very, very close, but they can't quite get there. And so what we want to do is to use the atmosphere in some sort of jet engine, air-breathing engine, whatever, to try to help the rocket get over that first little bit. In order to get into orbit, you have to, with a rocket, put about 9.5 kilometers per second in. If you can offload that down to about 6.5 kilometers per second, you can make all this work. but the penalty is you have to go to Mach 5. And in the 1980s, British Aerospace, Rolls-Royce got together, I put together some interesting thermodynamics for these engines, which I'll come to in a moment, and all of that seemed to work, but sadly it didn't last. Margaret Thatcher was sort of running the country. Anything that wasn't directly related to immediate commercial return didn't happen. And of course that nice Mr. Kenneth Clark, who I will say absolutely nothing further about, because otherwise I'll probably get arrested, finally put an end to this particular project. And so, once that project died, two colleagues and myself, Richard Varville, John Scott, we in 1989 formed Reaction Engines, and we looked at Hotel and had a look what hadn't quite worked about it, because we were struggling with Hotel. And one of the problems that we had with Hotel is that the liquid hydrogen tank, 60 tons of liquid hydrogen, formed this very long forebody. And as you accelerate up the Mach number range, the lift on the wings falls off a sort of 1 over the square root of Mach number squared minus 1, whereas the lift on the forebody remains constant. And so at Mach 5, 2,000 ton-meters of moment trying to pitch this vehicle up. That's a small ship on the end of a meter rule, trying to pitch this up. And a massive load of hydraulics, flaperons, immense structures to contain all of that. The whole thing ran away. Hotel was designed to put 7 tons into low Earth orbit, but finished up putting about 7 tons of hydraulic systems into low Earth orbit. So it was a transportation for hydraulics into low Earth orbit. So Skylon, we solved that problem by chopping up the hydrogen tank and distributing it in front of the vehicle and behind, putting the engines on the wings instead of the base and moving the centre of gravity into somewhere near the middle of the aircraft. And of course it took on this long pointy shape, and most of you here wouldn't remember the centrepiece sculpture from the Festival of Britain in 1951, which was called the Skylon, hence its name. Skylon then is a space plane. This is what it's designed to operate like. Payload installed in a hangar, wheeled out, a conventional towing tractor on a runway. The engines start in air breathing mode and accelerate to a point where it transitions to rocket. Once it gets onto orbit, small engines in the rear of the vehicle actually do the orbit insertion. It can deploy the payload, in this case an upper stage carrying a satellite. It then re-enters, quite high altitude, but I'll come to this later, and then lands. So that's just a quick view. We'll come to this in more detail, but that gives you a quick scenario. Once it's landed and turned around, it can do it again. No pilot. It's completely automatic like any rocket. There are good reasons for that. Saves weight, saves costs, and also there is no power at landing. It's what we call a dead stick landing. So it's gliding in to do its landing. What makes all that possible is the Sabre engine. So let's have a quick look at the anatomy of a Sabre engine. Well, it's a combination of rocket engines and a jet engine in effect. So here's the inlet to the jet engine. What enables that to be possible is the following. An ordinary jet engine is fine until you get to around about Mach 2.7, at which point, as you decelerate the air to go into the engine, the kinetic energy gets turned into heat, and the air temperature goes up, therefore the compression work is increasing, and also the temperature is increasing, so you run into the limit of what materials you have to actually pull this trick off. But the great thing about liquid hydrogen, which is the main fuel that I've been talking about, is that first of all it goes into the tanks at sort of minus 250 degrees centigrade, and secondly it's got 3.5 times the specific heat of water. So as a heat sink, it is a tremendous sort of boon to have on a vehicle. And we can effectively use the liquid hydrogen to cool the air in this heat exchanger. So the air comes in 1,000 degrees centigrade here when it's decelerated from Mach 5 through this heat exchanger, and in 1/100th of a second the air's down to minus 140 from 1,000 degrees C. Before going into this compressor now, when the air's at minus 140, the compression work is extremely low. So you can actually compress this in this compressor assembly here through a pressure ratio of about 140 and put it into these combustion chambers at about 100 atmospheres. So the same combustion chambers that you're later going to use as rocket engines will also serve you in air breathing. So you can actually stitch this air breathing engine and the rocket engines together into a single propulsion unit with a lot of common hardware. And then when you're travelling at Mach 5 and 26 kilometres, everything is getting very, very difficult to hold together. The air is very hot, the heat transfer into the vehicle's climbing, the drag's going up. So the answer is to turn off the air breathing part and to switch on the rocket engines. So this is the actual engine cycle that we're talking about. Here we've got an air intake. So the air's coming in at Mach 5, is decelerating, getting hot, and we then cool it. So it can be compressed and delivered to a combustion chamber and something we call a pre-burn. So this is the hot end of a thermodynamic cycle. The fuel, the liquid hydrogen, acts as the cold end of a thermodynamic cycle. And the vaporized hydrogen drives these two turbines, and you'll see in a moment, and the fuel supply arrives at the combustion chamber and hot gas down to the main combustion chamber. Let me just see if I can backtrack that a little bit so that we can run through it again. Okay, so that's the air cycle again. And in a moment the hydrogen will come in, so I can just go through that bit again. So here's the hydrogen pump, cold source, a couple of turbines, and that meets up with the air, and hot gas then goes to the combustion chamber. Now in between this sink and this source, we put a helium circuit like so. So it's heated by the air at Mach 5, we top it a little bit here, it drives the turbine, we cool it, compress it and so on. And then when we get to the rocket operation, we simply, I wish it did vanish like that, save a lot of weight, but what actually happens is we switch it through the turbine that drives a liquid oxygen supply from the vehicle. And then we can completely ascend into orbit. Now, this heat exchanger here is actually a phenomenal piece of engineering, and this is what it takes to make a heat exchanger like that. So we start off with a lot of tubes which are about 1 millimetre diameter, and they have a wall thickness when we get them of about 40 microns. Now that's quite thick. The final heat exchanger walls are down to about 20 microns. And those tubes are going to contain helium at 200 atmospheres. So what we do is assemble a bunch of tubes like that by brazing them into a series of headers and form a modular heat exchanger like this. Here you can see a series of heat exchanger modules about to be made into this structure. And here you can see a particular module about to go into the vacuum brazing furnace to finish up something like this. Each one of those modules is about £100,000 worth of engineering. And in this particular heat exchanger, which is a demonstration, there are about 21 of those modules. So I'm sure that you can do the sums on that yourself. The tubing at the present time costs us about £17 a metre. It's made out of Inconel 718. In a real engine, there are 2,000 kilometres of tubing in each heat exchanger. So this is really impressively expensive engineering, reassuringly expensive indeed. So we put one of those together and then we managed to get it on test. So what we do on test is that here we have a Viper jet engine and a silencer in case we disturb Steve Cowley's physicist working on fusion. And here we have a boiler in which we transfer approximately a couple of tons of liquid nitrogen, and that acts as our source of cold. And this circulator here circulates high pressure helium out to this experimental heat exchanger and then brings it back. We use the nitrogen to cool it. And if you look through the cameras in here, this is what you see. And what you're seeing there is the very, very cold air at minus 150 degrees C, and it is the heat exchanger sandwiched between two dummy sections, so that ordinary moist air gets drawn in, and you can see the cloud bank that forms when the air with ordinary moisture meets this extremely cold flow. Now, of course, we have to arrange it so that the very, very cold air doesn't freeze and block up the pre-cooler. If you don't do something about that, it takes about 5 seconds, give or take a second, to block a heat exchanger completely solid. And I'm afraid I can't tell you how we do that. That's one of the sort of secrets that we keep very, very close to our chest. But this is what we've actually managed to achieve. So back in 2012, since then we've managed over 600 tests, 300 at cryogenic conditions. Minus 150 degrees C is our lowest. Now, unfortunately, we didn't optimize the frost control system quite right, and so we can only operate with our present system at about minus 120 degrees C in a steady state condition. We've demonstrated the frost control system, and we've demonstrated the cryogenic cooling. The most important part is that this heat exchanger is flow stable. It wasn't clear that that was going to be the case. Of course, it operates in a fluid dynamic regime, which we call transitional, between turbulent and laminar, whatever that means in a heat exchanger at this time. And then also we've demonstrated that its thermal and mechanical characteristics are precisely what we need. It's extremely robust, despite the fact it has this extremely thin wall tubing. This has shown that we can take it up and down from our assembly area, and indeed in 2012 we carted the whole thing off to Farnborough and put it on display, much to the chagrin of some of my colleagues. And the most important thing is that this is partly funded by the European Space Agency, and we've met all of the objectives of their programme. Now, obviously, to bring an engine like this about, there are lots of other technologies. So back in 2008, we demonstrated the properties of a contra-rotating turbine. Heat transfer in the combustion system, very, very important aspect. We've worked with DLR in Germany and also Astra in Germany to do that. University of Bristol have done a lot of nozzle work. I'll come back to this one in a little while. Air intake models we've tested, and conditions of very high pressure in a so-called Ludwig tube configuration, and other types of heat exchangers. We've also done some clever nozzle work, and I'll come to that in a moment, and of course a whole series of heat exchanger stuff, starting back in 1996 at the University of Bristol, when we first demonstrated that we could achieve over 1 gigawatt per cubic metre in terms of heat transfer. Now, one of the problems with a rocket engine that's going to go from sea level to vacuum is that it has to have an eye-area ratio, area of the exit divided by the area of the throat, if it's going to achieve a high exhaust velocity in vacuum. And I've already alluded to the Tsiolkovsky equation, which says that the exhaust velocity of the engine is extremely important. And so we need area ratios of about 120. But the difficulty there is that the flow separates at sea level, and sometimes it can separate unstably. So we did a lot of work with this type of engine, which is known as an expansion deflection nozzle. So instead of a simple orifice for a throat, this actually has an annulus slot, and the flow comes out as a very thin jet, an annulus stuck to the wall, and operates very, very stably at sea level. And as the engine goes up in altitude, the core of that annulus fills in until at some particular altitude the core is then running solid, and the engine then is unaffected further by atmospheric pressure, except that you lose the pressure that's retarding it over the bank, so the performance increases like a normal rocket engine from that point forward. Now, there have been very large number of different Sabre variants, and back in the HOTOL days, first of all, there were some conceptual studies. I've already shown you an image of HOTOL which embodied the Rolls-Royce RB545, which was a rather primitive version of these cycles. And then there have been various variants, and the one I'm telling you about tonight is the Sabre 3 variant, and that's the one that we've got out in the public domain. But what I can tell you is that for the last 3 years we've been working on the Sabre 4 variant of this engine. And the main characteristic of that is that during the air-breathing ascent, we've actually managed to halve the fuel consumption. So the Sabre 4 opens up performance possibilities that even I, at the start of this project, never thought possible. So a vehicle which can take off from some airfield in Britain, having had its payload installed, fly down to an equatorial site, be filled with liquid hydrogen and liquid oxygen again, and then go off to orbit and do its job. So the capabilities of a Sabre 4 engine are really quite extraordinary. I want to say something about Skylon and some of the other possibilities that these engines now enable. I want you to imagine that you're somewhere down near the equator, on a launch site there, and there are a whole host of competing operators, Easy Space, Johnson Space, and so on. And one of those operators will be in shared facilities. The upper stage that you saw earlier with its payload is installed into the payload bay, and then the vehicle is taken by its towing tractor out onto the runway. At this point it's empty, and of course there's no pilot, as I've already alluded to. On the head of the runway, automatic systems fill the vehicle with liquid hydrogen, liquid oxygen, helium, inert all the inner spaces with nitrogen. And then the vehicle starts up in jet engine mode, effectively. And that accelerates it from the runway up to a speed of about Mach 5 and at 26 kilometers. And the heat exchangers are operating all the way through this. So there has to be that pre-burner in there which provides the heat while the incoming air is not hot enough. So just to recap then, it's a collection of rocket engines, combustion systems, the bit that is the compressor for the jet engine, and then this all-important pre-cooler. That is the key technology that this engine has. There's also a bypass system and bypass burners. I've not got too much time to go into that at the moment. And then the propellant systems, the liquid oxygen, the blue bits, and the liquid hydrogen. So here the vehicle's transitioned to rocket mode, and then that pushes it to a transfer orbit, and then you will see that the orbital manoeuvring engines here are then circularizing it in orbit. Once you're in orbit, you open the payload bay doors and then magically throw out a space telescope, which I must get somebody to amend this video sometime. But this is intended to show you the range of payloads, including CubeSats, that this vehicle could deploy with a little bit of artistic license there. So now, magically, we've got the upper stage and the ComSat back. The upper stage then puts the ComSat into its transfer orbit, but the stage doesn't circularize. It deploys the spacecraft and lets it do the circularization burn. And the upper stage, therefore, remains in an elliptical orbit, which, from a 300-kilometer base orbit, it turns out that this is in a 7-to-1 resonance. So Skylon orbits 7 times, and if by magic the stage reappears next to Skylon on Skylon's 7th orbit, where a gadget captures it, puts it back into the payload bay, and then returns the whole thing back to Earth. So once you've done that, you can return. This is going to show you a little bit more. We chose the payload bay so it could do a lot of things. This is a passenger logistics module, and that can carry between 20 and 30 people up to the International Space Station. So this would extend the life of the International Space Station. And since it's a $100 billion investment, then I think that would be quite important to do. We can also set up small laboratories in space and transport nodes. Now, there will be some vehicles which Skylon can carry into orbit, which then stay in orbit forever, and Skylon simply carries the propellants up to them. And a stage like this could service 15 tons to geostationary orbit, but also out to the moon, and set up possibilities of the moon. And we could even put very large assembly facilities in orbit to build vehicles for reaching out to Mars. And that's one of the most exciting things. We did a very comprehensive study of that called Project Troy, because a young lady named Helen at Reaction Engine sort of suggested we should do it. And there's the re-entry and the landing that I mentioned. On the vehicle, although we're an engine company, we have done a certain amount of work, so trajectory model and avionics, and re-entry modelling. Now, any of you who know anything about sort of re-entry vehicles will say that shape will never re-enter, it's all pointy and got bits sticking out from behind the bow shop. And the Germans at DLR sort of said this, they said we don't believe that that can be re-entered. Now, we've done quite a lot of analysis of that, we're convinced that it would. But DLR have got one of the best codes going, a thing called TAU, to do that sort of modelling. It usually takes about 3 weeks to do a computation. So we sprang them about 50,000 euros and they went off to model it. And indeed, not only did they confirm that it is re-enterable, they also showed that the re-entry environment is more benign than even we had calculated. So when we talk about this now, the phrase poacher turned gamekeeper comes to mind with DLR, and we have a great deal of difficulty stopping blooding all this at international conferences and so on. We've also done wind tunnel testing. This is Kingston University. One of the most interesting things that determines this configuration is the fact that you might have to land it in a gliding configuration on a runway with a 30-knot crosswind. And so the subsonic testing of this at Kingston was actually quite important. And then when we still had wind tunnels at Farnborough, we managed to get quite a bit of work done in those. And we've got ongoing work on structures taking place at Cullen at the moment at Reaction Engines. So this is silicon carbide reinforced titanium, and this is silicon carbide reinforced glass ceramic for the aeroshell. So there's an ongoing program of stuff on the vehicle. But some of this, of course, spins off into other areas. One of the important studies that we did was this vehicle, the A2, and that's a passenger-carrying aircraft that can carry 300 passengers from Brussels to Australia in 4 hours and 40 minutes. So it takes off from Brussels, it can fly subsonically out over populated areas. It can then go out into the North Sea with right hand down a bit and across and through the Bering Strait, down the Pacific. So from start of roll in Brussels to wheels down in Sydney is 4 hours 40 minutes under air traffic control conditions. Excuse me. And you can turn the aircraft around in an hour or so and then have it back at Brussels before the airport closes in the evening. Now that's quite an important thing to do because that affects the economics of the whole of that kind of operation. And it's quite likely that about 10% of air traffic would go that way. And the engine that allows that is this, which we call the simulator. It's a development of the Sabre, so you can see it's got a pre-cooler, it's got a compressor and combustion system. However, it doesn't have the rocket feature. It doesn't need to go to orbit. So the optimization of an engine like this is very different. I told you that on the Sabre, we're up at over 100 atmospheres in the combustion chamber. This has got a combustion chamber pressure of about 8 atmospheres. And that alters the economics of the whole of this. Sabre engines are phenomenally thirsty on hydrogen, but this one is actually quite economic. And we built some heat exchanger modules, which are quite different to the Sabre ones, to show that it could be done. Now, one of the problems is that the combustion temperature in this chamber is about 2,600 K. And that means the oxygen and the nitrogen react and form nitric oxide. And of course, NOx is very much a no-no. So we had a job from the European Space Agency of could we actually solve that problem. I mentioned earlier this staged combustion device, and that's it actually on test. And what we showed is that we could actually get the NOx produced well below the levels at which it could be detected in the exhaust. And we do that very, very simply. We simultaneously accelerate the flow while the combustion is taking place so that the static temperature of the flow never exceeds 2000 K. And that's proved amazingly successful with regard to that. The bad news is you lose some of the total pressure in the flow. But it turns out that this vehicle still has complete antipodal range anyway. So this vehicle can not only do 21,000 kilometers at Mach 5, it can actually do 23,000 kilometres in that engine configuration subsonically. So it's got all the go-around and landing capability that Concorde, in fact, never had. So finally, I want to try to take you through some of the other things that we've got. Diversification. When you've got 160 shareholders who've pumped several millions or tens of millions into your project, they're very interested to know how they're going to get their money back. And diversification is something I get bombarded with all the time. Space access, we've talked about. Hypersonic transport, we've talked about. Now, it turns out that these heat exchangers can be used to improve ordinary gas turbines as well. Time precludes me from going into that very far. But one of the most important simple things you can do is cool the air that cools the turbine. At the moment, modern engines are getting such that the air delivery temperature from the high-pressure compressor is such that using it for cooling is getting a bit of a joke. So if you put a heat exchanger in, use the external cold air, you can cool that air and improve that a lot. And then finally, a large market is desalination. The use of these heat exchangers makes possible all kinds of ways of making potable water from salt water or from foul water, and that looks like a big market. So we've recently launched an internal diversification program in reaction engines to try to capitalise on those things. The future. Okay, you recognise this guy, I hope. These are three of our apprentices, that's my good self. Everything was going fine until last July, when George Osborne turned up at Reaction Engines and said, the government's going to put 60 million into your future development programme. And of course that completely caused chaos. We've been working on the government for several years, but we didn't expect it to come so quickly. So all of a sudden we find that this is now getting serious, and we're in the process of looking at a 360 million pound 4-year programme for the next stage of development. So let me say something about the crew at Reaction Engines. Back in 2000, Reaction Engines was 3 people, and today it's over 60. And we've got manufacturing facilities currently in Newbury and Wantage, but also we've had experimental manufacturing facilities in Abingdon, which are now on the site of Cullen. And as a company, these are all the specialisms that our company actually has. We're very careful on the people that we've brought into the company up until now. And so this isn't just one guy who happens to know something about it. A number of these people can address each of these things. So we're a very specialist company and quite highly skilled. We're on the site at Cullen, so at the moment we are located in this building here. This photograph actually applies to that building, but don't worry about that. And then over the rear here we've got quite a large assembly area. And at the top of the site, the north end of the site, we have our actual test facilities. As you can see, this is a World War II air base, Fleet Air on base. And of course, Steve will recognise what's going on over here. These are the jet buildings, and we're right next to the 400 megawatt power supplies that come into drive jet. But we've also, I've shown you quite a lot of combustion experiments. We don't do those at Cullen. We work with a company called Airborne Engineering, which is we're quite proud of. We've managed to help them to grow out of the work we're doing. And so here at J site, you'll see that this is also a World War II site. All of the experimental combustion work has taken place so far. But excitingly, there is an area here called K site, and this facility here was put in the 1950s for test firing Polaris missile engines. And since the 1970s, this has been sitting dormant, and you can see a tree growing out the top of it up there. Somebody couldn't find where to put their old fridge, so obviously carted it in the back of their transit and dumped it in there. So we are in the process of finding out whether we can bring this site back to life. And at the moment, I don't know, because over here is Westcott Village, and we're planning to fire an engine with about 120 tons thrust on that site a number of times. So we've obviously got an interesting PR job to do. Back in the 60s and 70s, when I used to work on this site, with liquid hydrogen and so on. Nobody gave a figure about what went on, and the noise was regular. And indeed, we even fired RZ2 on that site, which is a 60-ton thrust engine. And all that we had on the main road was a little sign saying beware sudden aircraft noise. And that was the way it was back then, but I'm afraid you can't do that anymore. What's it all going to cost? Well, Skylon is approximately a £10 billion programme, of which £6 billion is the actual vehicle, and a £4 billion is roughly the cost of the engine development. Now, the bit that we want to do is this little sliver here, which is about 360 million. And this is the programme that we're currently at the end of phase 2, and we've called the next bit, very excitingly, phase 3. And that's going to be approximately a 4.5-year programme. We've actually started this ramp up here already. And then coming after this is, well, you could have predicted it could be phase 4, which is spending the rest of that chunk of money up there. Well, everybody likes to sort of know about this, but I mean, it is genuine. We all like to put up PR things, but these are really things. So, jobs and skills transfer education. I've already shown you the reaction engines that invested heavily. We've got a number of PhDs to our credit, and those apprentices that we got George Osborne to press flesh with. And in fact, our apprenticeship scheme is one that we do jointly with the Atomic Energy Authority. So we're very, very proud of that. We have job training programs. We're engaged in sort of regional growth programs. And one of the things that we've got is a supplier base. Obviously, we're a very specialist company, and that reaches out right across Europe at the present time. So, final slide then, and I think I'm more or less at the end of my talk. How does all this work economically? Well, in the past, the model has been some friendly government stumps up the money, you develop a launch vehicle, you wipe out the cost, and then you get somebody to operate that under semi-commercial conditions. Now, those days are going. I've already pointed out to you the immense cost of expendable launch vehicles. So the model we've got is slightly different. There are a lot of people around the world who would like to have their own access to space. And the different depths of red on this diagram are people with strong interest. White is where there's no interest, pink is some interest. And you can see there are a lot of places around the world where people would like to have frequent, regular, cheap, reliable access to space. And so the model we've got is develop the aeroplane and the engines and sell it to them. And so a Skylon costs a bit short of about £1 billion if you want to buy one. But a development program of an expendable launcher is many, many times that. So if, for instance, Argentina want regular access to space, they buy a Skylon for £1 billion. That gives them 200 missions into space. A Skylon is only designed to last about 200 flights. Brazil is also, and Brazil are interested in providing that equatorial launch site that I showed you on the video. India and China are in the process of getting into a space race, which, according to their own PR, is going to make the space race that took place between the Americans and the Russians pale into insignificance. Now, whether that is actually going to happen remains to be seen. Of course, up here in sleepy old Europe, we've still got a requirement for access to space. And even in Britain, we, over the past 30, 40 years, have developed the use of space services. And in fact, I think even today, we are the third largest user of services that come from space, mainly telecommunications, but meteorology, surveillance, and things like that are really cornerstone of what we do, and of course pressure. That's our market. We think there's a market there for 30 vehicles, and that 30 vehicles justifies the whole of the development cost. What about the actual cost of a mission? Well, we think we can bring the cost of a mission to between $5 and $10 million. That's still pricey, but compare that with the 180 million if you wanted to go by Ariane 5 at the moment, or with the 700 million that was the shuttle access to space cost. Skylon could only carry 15 tons, whereas the shuttle could carry 24. But even so, we're talking in round numbers of an improvement of a factor of 50 in terms of access cost to space. In terms of reliability, obviously people have got huge dreams about going to Mars and things like that. But an expendable launch vehicle, it arrives, as I said, as a kit of parts. You put it together with all the practical quality assurance. About 1 in 50 expendable launch vehicles finishes up in the nearest ocean instead of going into low Earth orbit. Now, at entry to service, we're trying to get that down to 1 in 20,000 with the Skylon. But Skylon's got an important characteristic that those launch vehicles don't have. It can abort its mission. And at entry to service, we expect to hit an abort rate of about 1%. So 1 in 100 doesn't make it to orbit, but what it does do is make it back to its base. And as you fix the failures that cause the abort, the reliability improves in service until you reach a magic number of 1 in a million, because at that point you can put people on it, and the vehicle loss rate then falls to the sort of loss rate of military aircraft. So Skylon becomes cheap. In terms of reliability, it's great, but what about in the lead time to get a mission? Well, currently, if some astrophysicist wanted to get a mission into space, it would probably have to book that launch 18 months to 2 years in advance. With a Skylon, he or she could pick up a telephone, phone around a couple of launch companies on a Monday morning, and by Friday their payload would be in orbit. And so that's the sort of change in technology that we're trying to bring about. And on that note, I will be quiet, and if anybody's got any questions, I will try to answer them. Thank you very much.
Well, thank you, Alan. I think we have quite a lot of time to do the questions. So who wants to ask the first question?
Okay, so I was wondering, you have so many compressors in your engines. I've seen on the internet things like scramjets or ramjets, which are basically have no moving parts at all, except for some rollers so that.
Yeah, they're wonderful, aren't they?
Yeah, so, I mean, I know they don't work, and like.
That's a downside, but there are other aspects to it. In that, many years ago, my mentor was a guy named Val Cleveland at the Rolls-Royce Rocket Department. I went into him one day and said, "Val, what about scramjets?" I still have the imprint of his boot in my backside. And he then set to give me a very long lecture. So when you're thinking about things like that, they only operate when they're flying at high speed. And therefore, what does the development program look like? Well, over here you've got sort of £20 billion worth of wind tunnel facilities to build before you even start to think about the development of the scramjet itself or the ramjet. Ramjets are a little bit easier. Whereas the engine technology I've been showing you has one characteristic in common with all other useful prime movers like piston engines, jet engines, rocket engines. That is, you can take them outside, you can put them on an open air test bed, and you can then start the development program. And that has an amazing impact on the development cost. So the only reason that that development cost is 10 billion and not 20, 30, 40 billion is because we don't have to build all of those facilities to do the development work. With a scramjet, you need a wind tunnel which will get you up to about Mach 4 with a full engine flow in order to and then handle the exhaust. Now we're talking about massive facilities to do that. So it's the development side of that is really the big impact. But then one of the problems with scramjets is that the intake and everything has got to be full of variable geometry in order to get all of the combustion system working at exactly the right condition. The difficulty with both ramjets and scramjets, if you've got a mismatch in the efficiency of the components, they become drag devices and not thrust devices. And so there's a huge problem developing all of that and get that to actually work. Now, sort of 20 years ago, we thought that combustion in scramjets was going to be really difficult because you've got about 1/10 of a millisecond, maybe 0.2 of a millisecond, to actually get the fuel into the flow and burn it as the flow goes through the combustion chamber at Mach 4. Now that's turned out to be surprisingly easier than people thought, and Now, there have been 1 or 2 flights in which for a few seconds ramjets have actually used, possibly, nobody's absolutely certain, net thrust, but that's at the end of incredibly expensive flight development programs. And I mean, we're at a situation now at Reaction Engines, although we've not built an entire engine, we've tested all sufficient components that we know that we can put an engine together, heave it out onto that testbed at Westcott, and demonstrate the whole thing works. Whereas the scramjet community has spent already billions and are still not very sure whether they generated thrust in its own manner. Stunning silence.
At a couple of points you said, obviously I can't talk about this because maybe it was classified, or I can't tell you the secret because it's something you keep very tightly to yourself, and obviously that's to some extent a commercial necessity for an organization like yours. But I was wondering to what extent there is collaboration, to what extent that secrecy is a problem for the kind of development you're trying to work at, and like, are there a bunch of organizations that are doing the same type of research side by side, but fear sharing that kind of research, or sort of how that works out?
Okay. I think the last point of that first is that nobody else has been doing research in this direction. And in explaining the engine cycle, I pointed out that the important part of these engines is that thermodynamically they're quite different to anything that anybody else has investigated. Even though I myself have been shouting the odds about them now for 30 years, it's actually quite difficult to get other people to take notice. A little bit of success, such as we announced in 2012, that the heat exchangers actually work, and then George Osborne coming and give us money, has caused a lot of people to suddenly sit up and say there must be something happening here. And about a month ago, we signed a collaboration agreement with the United States Department of Defense Air Force Research Laboratories. And so what is happening at the moment there is that they are checking to see whether these funny cycles do actually work. Now we know they do because the Italian company Avio and the European Space Agency did their own independent checks on this years ago. So we're not in any sort of danger of that coming unstuck. So we are hoping that between end of March, end of May, the AFRL will come back and say, yes, this cycle works. Now, there are real difficulties working with the Americans these days. They have an insidious bit of legislation called International Trafficking Arms Regulations, and they are paranoid that American technology is going to be used in some future system against them. So since 9/11, that has really tightened to the point where it's doing them a great deal of harm, but it also scares the willies out of the rest of us, because if we get the slightest bit of American technology into our program, then we would be subject to American legislation, even though we're not Americans, and they could do a great deal of difficulty to us, giving us a great deal of difficulty. Now there's an example of that in that Thales Alenia have been building satellites for the Chinese, for example, and they've been using catalogue components, some of which are American supply, and the American government has retrospectively classified that as intolerable and stopped Thales Alenia supplying satellites to the Chinese. So working with the Americans is a very double-edged sword on that. Clearly they have got several things we don't have in Europe. The first one is a joined-up government which deals with a very large economy, whereas in Europe we've got a government that I defy anybody to claim is joined up in any sense whatever. So actually getting anything done on that scale in Europe is really, really difficult. So we have to engage with the Americans, but there are all kinds of difficulties associated with that. Now, moving forward on that, we are in dialogue with a lot of European industries now who do want to be part of this project. So they're not competitors, but what we will probably finish up with to develop the engines and the vehicle is some sort of consortium. Reaction Engines is not interested in the vehicle as such. We're interested in knowing what its technology is, what it weighs, what it's going to cost, because that's all part of the overall program. but we need a prime contractor to sort of adopt that and look after it. And I'd like to think that one of the European airframers will do a European vehicle, and it's clear to us from the dialogue we've had that a number of American airframers are interested in doing an American vehicle. With regard to the future on the engine development, I think it's clear that we can form a European consortium to develop engines for Europe, but we will probably have to create a US subsidiary of the company to actually build the engines for the American vehicle, assuming that that goes ahead. So from a business perspective, it's a very exciting time, and to some extent outside my comfort zone. So other people now in reaction engines are now starting to adopt the responsibility for worrying about all of that sort of stuff. I hope that answers your question. It's really quite complex.
Almost 25 years ago, roughly, you left a big company job to start this project with the vision that 25 years later you would maybe not be talking about it, but at a stage that you were like now.
I thought it was 5 years later at the time.
Okay, so it's an actually vast scale thing. Where at that time? So obviously now you've got some money from the British government. Maybe you could say maybe 23 years. Too late. Where has all of that vision and money and everything come from? Has it all been from your initial idea?
Well, the vision came from Dan Dare in the Eagle back in the 1950s. And I thought, well, we've got to have some of that. Prior to that, I'd been interested in astronomy like a lot of kids, and suddenly I realised that I don't have to sit on the end of a telescope and look at it. I can actually sort of get out there amongst it. And that was where the sort of vision started. So all my time at Rolls-Royce and then later at British Aircraft Corporation, and even at the Atomic Energy Authority, I was involved in looking at how we bring all that about, the bigger picture, because it might be difficult today for you folks, particularly you younger ones, looking at it, to sort of feel that there could be an alternative, but we were really sort of sidetracked by the availability of Cold War weaponry. We never planned that it would go down the route that it's gone down. Aeroplanes were going to get faster and higher, and eventually the pilot would find himself in orbit, and it would go from there. So that bit of the vision wasn't really mine. That's how we grew up to expect it. With regard to the money, that is where the major part of the difficulty arises. The engineering is really, really easy compared with getting cash and pulling all this international politics together. Obviously, we've gone through various phases in the last sort of 30 years, from sort of extreme financial services and all of that sort of thing. Engineering is dead. We've had politicians, in fact, talking about, I remember Wedgwood Ben saying technomania is passing back in the 1960s. And then we were going to deindustrialise Britain in the 1980s and 90s. And damn near succeeded in doing that, only by a fine thread, as it actually survived that sort of extreme. And so today, we can't even afford to do today what we used to do in the 1950s and 60s, which is a bit of a mystery. But the thing is, we've sort of lost the bogeyman under the bed. Back in those days, we were first of all scared of the continent, and then we were then scared of the Russians.
Well, that's coming back.
Sorry. Nothing motivates politicians like having somebody to be frightened of. And so the Cold War, obviously, was probably good news, but to some of us, we often think, was it really good news? Because since then, an awful lot of progress that the Cold War motivated has actually stopped. And certainly the flow of money to support the new research and so on has decreased dramatically. Now, I don't know, I'm biased, I'm impatient, I'm running out of gears, and I want to get on and do it. And I think from what I've shown you, you've seen the Reaction Engines as a company that does go away, cut metal, and actually do things rather than muck about with paper studies. But maybe there is an argument that says that it should all go a bit slower, and we should all take our time a bit more and attend to situations more equally distributed between here on Earth and expanding off the planet. To me, I think the clock is ticking. Our population is not under control. We are going to peak at, I don't know, 10 billion maybe 12 billion, a planet with very limited resources, when just out there, only 250,000 miles away, is a massive resource base. And if we can get to it, then we don't have to destroy the Earth in supplying the resources that are needed. However, if you use models based on things like the Club of Rome and so on, you will find that we've got a very narrow window to actually achieve that. And therefore, I do think it's imperative that we find the funding and get all this technology in place now, so that we've actually got it and it can be used. So I do think that's important. Where's it going to come from? Well, various places, the industries, sovereign wealth funds, governments, and so far, in our case, 85% of our funding has come from high net worth individuals. I've mentioned our 160 shareholders. They're a mixed blessing because obviously they don't give you the money and as a philanthropic sort of gesture. They expect to see profit out of it, and somehow we've got to put together a business case that shows how that can be achieved. We tried very hard to do that, with great or lesser success, but 30 years on we're still here and sort of it's still going.
Well, one of my slight queries was that, so you talked about the research and development being many millions of pounds and saying that was a big number, but if you compare that to just say one pharmaceutical company,
Yes.
like GSK,
Yeah.
that's a yearly investment for them. They invest that much a year in
Absolutely,
research and
but I mean,
development.
it's one of the mysteries of our economy as to how some areas like that, billions are sort of chicken feed, and in other areas getting sort of 30 million to do research on fusion, which you might expect is sort of high on somebody's priority for the future, is very difficult.
I mean, did you want to sort of approach a big company that already existed and ask them, could you be like an arm of a new project that they would do? Was it that there were no companies in that field?
We try all of that and get varying degrees of answer. Some of them fairly blunt, and others are sort of conciliatory, and we're still talking to them. Watch this space and we'll see what the final answer turns out to be.
How long a runway does Skylon require?
How long a runway? Quite long one. Because we try to save weight on the vehicle, we don't put high lift devices. If you sort of look out of your aeroplane windows on takeoff, you'll see the wing sort of falls apart into a complex shape and then magically reassembles itself in flight, and that keeps the runway length down. We can't afford the weight for all of that, so we choose a simple-minded option of simply accelerating the aeroplane up to Mach 0.5 on the runway. And as a consequence of that, a normal takeoff run, if everything goes well, is about 2.7 kilometres. But if as you're about to rotate, one of the engines sort of sputters and goes out, then the international regulation is you've got to clear the 35-foot fence at the end of the runway. And so that means that the runway's got to be 4 kilometres for Skylon's acceleration rate to actually give it sufficient clearance over the 35-foot fence. But then another alternative is if you've not actually quite got sufficient flying speed to get off the runway, then you have to stand on the brakes in order to decelerate it. Now the kinetic energy when you're up at 300 meters a second, 150 meters a second, 300 knots, is approximately 3.3 gigajoules. That's 3/4 of a ton of TNT that you've got to dissipate somewhere. So on Skylon, what we do is carry about 1.5 tons of water to cool the brakes while we're decelerating. On a normal takeoff, we throw that away so we don't carry it into orbit. But the bad news is that you require yet another 1.6 kilometres of stop weight. So add that to the 4 kilometres you've already got, and we're looking at a sort of total runway of about 5.6 kilometres. Now one day, as I said I gave a tantalising hint about the Sabre 4 engine and the vehicle that's in is called Skylon configuration V1. We can possibly afford to start looking at putting some high lift devices on it and drag that runway length down, but that's a little bit in the future. At the moment, runway is cheap and high lift devices are expensive, so we'll probably stick with that.
So you said that the use of these reusable space planes will allow people to get off the Earth and go to other your map there, you know, there are many countries who are interested in it, and some countries, you know, I suspect, you know, probably Iran, maybe, you know, other companies with, countries with, say, nuclear weapons and stuff are interested in this thing, and so, you know, they would then be able to put into space if they wanted, you know, say, nuclear weapons. So do you think there's some potential here for an invention that's meant to, you know, save the human race to possibly do that?
Well, even today, there's nothing to stop Dr. No buying a ordinary aeroplane and sticking a nuclear weapon in it.
But you know, if you could put such a weapon in space, you know, for such a regime, you'd be able to, you know, send it down at a much faster speed.
I mean, first of all, it's very difficult to target a nuclear weapon onto a precise target. There's something called the circular error probability, and even with very sophisticated guidance systems, getting that down to the sort of few meters required to actually kill a hardened target is very difficult. So Skylon's not an ideal platform for doing that, but various regimes can launch, including our own, can launch other payloads into orbit, which are much more important and interesting than the possibility of nuclear weapons. So electronic intelligence and surveillance satellites. Now, during the Falklands War, for example, and in virtually every little scrap we've got ourselves into, there have been surveillance satellites in space, but always in the wrong place. I mentioned a little while ago that you could have, with Skylon, on a Monday morning, you can sort of order your flight, and by Friday it can be done. Well, in a military context, then you can get that down to a couple of hours. So if you've got your Thunderbirds 2 hangar that's got all the payloads sat in there for doing different clever jobs, then if you find yourself in a diplomatic situation, then you can pick your payload and have that in orbit, in the right orbit, doing the job you want it to do. So that's a much more important sort of military objective, a sort of political military objective, than having sort of the ability to deploy nuclear weapons. Clearly, as has happened in aviation and with nuclear power, there will have to be agencies set up to monitor and control what people do. At the present time, I think it's fairly clear that there will be a limited number of spaceports from which these vehicles can operate. Ideally, for a commercial operator, it will be down near the equator, because from the equator, on Monday you can go into a sort of 0-degree inclination orbit over the equator, and on Tuesday morning you can go into a 98-degree inclination orbit to put a sun-synchronous satellite up. So you need to operate sort of reasonably close to the equator, but there is nothing to stop some military regime trying to do as you suggest and use it for some sort of clandestine purpose, but provided there's adequate monitoring. I mean, from orbit we can see incredibly fine detail on the ground as to what people are doing, and you can get inspectors in there to make sure that you've got control over it. But I can't feel that the human race has to be confined to this sort of blob of grot ordering or rather ordinary star, simply because we can't take control of a situation and get these vehicles operating. There's some questions.
You mentioned 2012, I think, proof of concept for the heat exchange units. Are there remaining proof of concept? Is there some challenge coming that you have?
Every day.
Well, do it another way. When is the first prototype?
That depends rather on the funding, but I'm hoping that in 4 years' time we'll have the first 2 prototype engines on test, possibly at Westcott, in the facilities I've already indicated. The first flights to orbit will take place maybe 2 to 3 years after that in an ideal world. Right at the present time, it looks as though the first vehicles could be delivered to customers around about 2025. So it's a 10 or 11 year development program, but the first vehicles would go to orbit about 6 or 7 years into that program. And we're currently just restructuring it because some possibilities, which I can't go into in detail, have cropped up for actually leapfrogging some of the early sort of flight development program with prototype vehicles. So there's some excitement there. Are you familiar with TRL levels? Okay, well, the engineering world in this area always talks in things called technology readiness level. So technology readiness level 1 is when you're sat in the bath and have a bright idea, and then the technology readiness level 9 is when you actually really get on the runway and start the engines. Now, we are somewhere around about technology readiness level 4 to 5 at this point in time, depending on exactly how you define it. Obviously, with a scale like that, it's quite hard to put your finger on it. The important point about that is your technologies are at the point where people will now take interest and start to put investment into it in principle. Now, in our case, people are really, really scared of the idea that here's a space plane, it seems to have magical capabilities, therefore should we really do it or not? And of course, the rest of the world is watching. We've convinced the rest of the world, and thanks to George Osborne, he added really the sort of icing on the cake, really convinced them. So out there we are almost certainly generating competitors, and therefore we have to move fairly soon. We in Britain are to stay ahead. I mean, we've got an exciting opportunity here. In relation to getting the investment in, if we can pull it off, then this is a whole new industry which Britain's got the lead in.
Could you just to make it precise, the 6 to 7 year time scale, is that the infinite money scenario or is that the real money scenario?
Sorry, is it the...
So the 6 to 7
Yeah.
Years time scale to launch,
Yes.
the first launch, is that the sort of infinite money scenario or the real money scenario?
It's not infinite money.
What's the infinite money scenario?
Well, infinite money is not really needed. What's needed is instant decision.
Arbitrary amount of money.
I mean, what we seem quite incapable of is making decisions, even if it's not going to cost infinite money. I mean, high-speed rail is going to cost far more than this program, 10 times as much as this program. Okay. So it's really, we need people who will stick their pin in the page and say, we're really going to do this. And that's, I mean, thanks to George Osborne, and in the past I've been publicly very critical of governments and their decision making, but David Willits is an outstanding leader of BIS at the present time.
So, during your talk you often emphasized that there will be no pilot on the vehicle. Do you think there might be scenarios, well, I'm sure there might be scenarios where human intervention may be of great importance in order to prevent an aborted mission. So could you think in the future that there might be missions or there might be vehicles where there's a pilot or at least a technician on board at every mission?
Yes, but he'll have his hands tied behind his back in case he touches the controls. It's unfortunately a sad statistic that 80% of aircraft crashes are caused by the crew. And having said that, there is no statistics which show how many times the crew have actually saved a situation. That's an unfortunate part of it. But it's certainly a statistic that 80% of crashes are pilot and crew error. So for many years now, when I used to work with British Aerospace, even back on HOTA in the 1980s, they would really, really like to get the pilot of even the aeroplane that takes you from Heathrow to Paris. They would much sooner that all that was automatic and computer controlled. But of course, passengers won't accept that. Everybody intuitively feels that they want some guy sat up front, ready to grab the joystick and wrest it out of danger. So, with Skylon, this is a delivery system to space. I don't think there's too much of an issue there. And even with vehicles like the Space Shuttle, I mean, yeah, there were pilots on it, but they didn't actually do anything other than turn the computer on and off. With the A2 vehicle, then that would be sort of rather more difficult to decide. And I think that provided a highly paid representative of the company that's operating the aeroplane is actually on there, then I think that might solve that problem. One of the more peripheral but side issues is the number of people that complain there are no windows in these things, especially the A2. I always make the point that with the advent of flat screen displays and so on, you can cover the entire inside and you can make the aeroplane disappear in the flight if you want to. So that would be a scary moment. That's another issue, but there are a number of operational issues like that, but the pilot is a liability. I hope there are no pilots in the audience. You you've got to be careful how you say that down at some of the research places.
So you, correct me if I'm wrong, but you mentioned that if the plane lifts off, if Skylon lifts off and something goes wrong, it can get back home.
Correct. From
and
every
yet-
conceivable engine failure.
Okay, so how is that done? Because you also mentioned that nuclear missiles only have like a certain radius. So how can it get back to the runway? Is it remote controlled or?
Well, it's autonomous. It's got in the computer various support strategies. So, for example, if the aircraft takes off and it finds that it's got an engine on each wing, if it finds that one of the engines is dicky, it shuts that down whilst it's in air breathing mode. It actually has to yaw slightly so that the good engine's trailing, and then it flies a route back to the base, ditches all the liquid oxygen and most of the hydrogen, and then flies to a powered landing under those circumstances. If it's already gone to rocket mode, the engines are configured so that in each nacelle there are effectively 2 rocket engines. There's only one air-breathing engine effectively, but there are 2 rocket engines in each nacelle. So if one of the rocket engines is misbehaving, then because there's no aerodynamics to help you with the control, you have to shut down the bad rocket engine and shut down the corresponding good rocket engine in the other nacelle. And at that point you've then got several options in those circumstances. If you're far enough into the ascent, you continue, go almost into orbit but not quite, and do a complete once around and re-enter in order to get back to the base. Alternatively, you drive the vehicle to a point where you can then do a banked re-entry, and you pull aerodynamic lift while the vehicle is decelerating and pointing itself back home. And then those bypass ducts that I've not been able to talk about this evening very much, they can act as rather poor manned ramjets. So you're coming down from quite a high Mach number. When you get to Mach 3, you light the bypass duct, turn off the main engine, and it comes home as a ramjet at Mach 3. So, and there are other scenarios, and in each of those scenarios there are overlaps so that the computer can make a decision as to what to do. Now that question is very, very central to an important function the government started 2 years ago, which is these vehicles got to be certified like any normal aircraft. And so how do you certify a space plane nobody's built one? And it's bringing a whole host of new problems. And so there is a so-called space plane certification workshop that's ongoing. And the question of the autonomous operation is the real problem. And they have that with the UAVs at the present time. So UAS is the current acronym. So that if you're flying some unmanned vehicle out over foreign territory and you lose the uplink to it, the vehicle has then got to decide what it's going to do about that. And this is really where the central issue sort of lies. As long as you've got a pilot on the ground playing with the joysticks and he's in control of the aircraft, nobody worries very much. But once you've lost the control and the airplane is now making the decisions on its own, that's where the sort of real problems come from. And so there is an issue with regard to the automatic people are reasonably comfortable with, autonomous, where the machine is making real decisions based on a whole load of input about its circumstances. That is quite difficult. What the answer to that is at the moment, I don't know. We're right in the middle of that at this point in time.
Yeah, I just wondered how robust are these engines? I'm just thinking in terms of this wonderful heat exchanger you've got with very thin walls, and what happens if a volcano with an unpronounceable name goes up and there's lots of dust in the atmosphere, and you know you're looking at this about 5 or 4.
We're not actually in a bad situation in those circumstances, because the problem with the unmentionable volcano, mainly because I can't pronounce it, is that as the volcanic ash goes into the turbine of a conventional jet engine, it blocks the cooling holes and so it forms a glass in the turbine, and that stops the turbine working. Our engines, the turbine is driven by helium, and that's in a closed loop, so that the high temperature part of the turbine doesn't see anything like that. The usual problem with things like bird strikes, if it swallows a swallow at takeoff and goes into the engine, what does it do? But again, the aerodynamic configuration is such that the air having entered our heat exchangers has to turn through a right angle, and the swan tends to go down the bypass duct and gets cooked in the bypass duct. But in the event that you get engine damage, then you go into the abort scenario that I just described and bring the aircraft back. With regard to day-to-day handling and everything, it's very, very robust, much more robust than I would have ever given it credit for. So it's handleable like a normal piece of aircraft engine kit. When it's depressurized, then it could be subject to damage. So if somebody sort of accidentally jammed his screwdriver into it, then that would write off a heat exchange. And the price of these heat exchanges, there's no question of being able to stock it out in salary or anything. So that is a real sort of issue. But once, it's a bit like the chips in your computer, when they're in the environment they're engineered into, it is absolutely usable, safe and robust, and you can throw it about. And we have done.
All right, so we have to wrap this up. I saw that there were a lot of students with questions. So what I suggest you do is we're about to go to dinner, and I suggest that people who have questions should form a little cabal with an empty chair in the middle at the table, and then we'll insert the speaker into that chair, and then we can come to the rest of the dinner. So organize yourselves. But now let's thank Alan for this excellent talk.